So to solve this FRQ problem, I will first read the problem. The half-life of the catalyzed isomerization of cis-2-butane gas to produce trans-2-butane gas, represented above, was measured under various conditions as shown in the table below. So before we actually solve this problem, I'm going to explain some relevant chemistry concepts. So first, we have to understand what a first-order reaction is, and that's a reaction with a rate that is linearly proportional with one reactant concentration. So that means it's going to follow the equation rate equals a rate constant times the concentration. And then the half-life is the time needed for a concentration to decrease to half its value. So for a first-order reaction, the half-life is going to be the natural log of 2 over K. And putting these two facts together, we know that the half-life of a first-order reaction does not depend on the concentration of the reactants, only depends on the rate constant. And the rate constant will change with temperature. And then finally, to solve part D, we need to know what activation energy is, and that's the minimum energy a reactant needs to undergo a reaction. And just a helpful graph, this is what a first-order reaction looks like, and if we graph y with respect to the natural log of the concentration, we get a linear line with a slope of negative k. So to start solving this, I will do A first. So for A, the reaction is first order. Explain how the data in the table are consistent with first order reactions. Well, as you can see, in trials 1 to 3, the temperature remains constant and the half-life remains constant, even though the initial concentration is changing. So what we can say is that these trials are consistent with first order reactions because when the rate constant stays the same, which is when the temperature stays the same, the half-life stays the same regardless of the concentration. And then trial 4, the temperature is different, so that means the rate constant is different, and that's why the half-life is different. So for trials 1 through 3, the initial concentrations of cis-2-butane are different, but the half-lives are the same. This is because there is a constant temperature, I spelled that wrong, temperature, which keeps the rate constant the same. And half-life is determined by ln2 over the rate constant. So for trials 1 to 3, the initial concentration of cis-2-butane are different, but the half-lives are the same. This is because there is a constant temperature which keeps the rate constant the same, and half-life is determined by ln over k for first order reactions. So that's why this data is consistent with the first order reaction. For B, calculate the rate constant K for the reaction at 350 degrees Kelvin. Include appropriate units with your answer. Well, as I explained before, the half-life for a first order reaction is equal to the natural log of 2 over the rate constant. So with some manipulation, by multiplying both sides by K, then dividing both sides by half-life, we get the rate constant equals natural log of 2 over the half-life. But then in our table we can see at 350 degrees, the half-life is 100. So if we do ln over 2 over 100, we're going to get, let's use a calculator. So ln 2 over 100, and that 100 is measured in seconds. So 100, we're going to get 0.0069693. And that's second to the negative 1. So our problem solving strategy was to use the half-life equation, reorganize it so that we're solving for the rate constant, and then we just plugged in our half-life right here, which was 100 seconds, and we got 0.00693. And then we plugged in seconds, so then we're going to get seconds over 1. So our rate constant is equal to 0.00693 per second. Now part C. Is the initial rate of the reaction in trial 1 greater than, less than, or equal to the initial rate in trial 2? Justify your answer. Well, as I explained, the rate of a first order equation is equal to K times A. And it's asking, is the reaction in trial 1 less than or equal to the rate in trial 2? Well, we can see in trial 1, our initial concentration was 300, and in trial 2, our initial concentration was 600. So, if we plug these numbers into this equation, it'll tell us the rates. So if we plug 300 into this equation, we're going to get 300 times K equals the rate. So rate equals 300 times K. And for the second trial, we're going to get rate equals 600 times K. And obviously we know K stays the same between these two trials because the temperature stays the same. So obviously the one with 600 has to have a higher rate. So therefore we can say that the initial rate in trial 1 is less than the initial rate in trial 2 because the initial concentration in trial 1 is less than that in trial 2, and the rate constant remains the same. So, because the second trial had a greater initial concentration, it's going to have a greater initial rate. And then for part D, the half-life of the reaction in trial 4 is less than the half-life in trial 1. I explain why in terms of activation energy. Well, as you can see in the table, the half-life in trial 4 is less than the half-life in trial 1, but also the temperature in trial 4 is greater than the temperature in trial 1. So what that means is the average kinetic energy of all the particles in trial 4 are going to be greater. So when they collide, they're going to have a higher amount of energy on average, so they're going to lead to more successful collisions, which allows the reaction to go on to occur faster. So what we can say is the half-life in trial 4 is less than the half-life in trial 1 because the average kinetic energy of the particles will be greater, so more collisions will occur in which the amount of energy is greater than the activation energy of the reaction. And as I explained before, the activation energy is the minimum amount of energy a reaction requires to occur. So because in trial 4 there's a greater temperature, all the molecules have a greater kinetic energy, so when they collide they're going to have more total energy, and so they're going to be more likely to have enough energy to overcome that activation energy. So I've answered parts A, B, C, and D of this problem, and I hope this video explained it well.